Alright, so the goal of this video is gonna be, I'm gonna show you the chain rule in higher dimensions, and we're gonna show the connection between the chain rule in any dimension, between the dot product in any dimension. So stick with me here. And these two concepts might seem, unrelated, because why would a dot product have anything to do with differentiation? Well, I'm gonna show you. So we know, freaking the chain rule in single variable calculus, which is that if w is a function of x and x is a function of t, then the derivative of w with respect to t is this product right here. Pretty simple stuff, this makes sense because dx and dx cancel out and we're just left with dw dt. But what about the chain rule in in functions of two variables? I'm gonna actually show you a quick proof for this instead of just the dx's cancel out. And for that, we're gonna need to come up with the rigorous definition for differentiability. Notice here that delta y here is approximately, keyword approximately, equal to delta L. We're assuming that delta y, delta x, delta L are like really small. Delta L is the change along the tangent line at xo. So we get that delta y is f prime of xo times delta x. And then we add in this error term because delta y is approximately that. This is because delta x could be like anything. Another way to show this is just by realizing that delta y on delta x is approximately f prime of xo here. So multiply both sides by delta x, we get this. And since we're dealing with finite delta y and delta x, that's why this is only approximate. We get that delta y is exactly equal to f prime of xo plus epsilon times delta x. We add epsilon to f prime of xo here because epsilon here is the error term. So we now found the error term, which is just epsilon times delta x, and we make this exactly equal because of the error term. And as delta y approaches 0, epsilon approaches 0, because if delta y is 0, if it approaches 0, then delta x has to approach 0, because if we divide both sides by delta x, then as delta y and delta x approach 0, epsilon should approach 0, because these two terms approach 0, then it's equal to f prime of xo. So we end up with this. If delta y is equal to this stuff, then f is differentiable. So now we have a definition for differentiability. Let's use that. So we have this equation that we came up with, and if we divide both sides by delta t, we get this. And if we let delta y, t, and x approach 0, we get dy dt is equal to this. And since here we let delta y approach 0, epsilon goes to 0 too. So we can just get rid of this term. So we end up with the chain rule that dy dt is dy dx times dx dt. And this is if y is a function of x and x is a function of t. So a function of a function. But what about for freaking higher dimensions? Well, that's where we need to extend the definition of differentiability to the third dimension. If we have w be a function of x and y, the mere existence of its partial derivatives with respect to x and y does not imply that w or f is differentiable. But in two dimensions, or y as a function of x, the mere existence of the derivative with respect to x or with respect to y or whatever makes the function differentiable. It implies that it's differentiable. So why are the three-dimensional cases and two-dimensional cases different? I had to hop into Desmos to show you this. The difference is because when we take a partial derivative, we're describing the curvature, or not the curvature, the slope of the tangent line of this trace here in the plane x equals x. And when we take the partial with respect to y, we're also doing that, but in the plane, or in the trace in the plane, y equals y. So we're just doing all these curves here. Yeah, that's cool, but what about any other plane? What about the planes that aren't parallel to the x the xz and yz planes? We could take the slices in literally any plane, and there is an infinite amount of planes to do this. So that's why the mere existence of partial derivatives does not imply that the multivariable function is differentiable. Because we could calculate the slope of the tangent line in the plane x plus y equals minus 1.6, or x minus y equals 3, or whatever. So we need to extend the definition of differentiability to ensure that the function is differentiable in all the planes. And there actually is an extension, of course, into the third dimension. And it's this right here. We call z is equal to f of xy differentiable if delta z satisfies this. Oh, and by the way, fx and fy here are they represent the partial derivatives of f with respect to x and y at this point, x, o, y, o. Now there's a couple reasons why this is the extension, and we know that it is the extension, but I'm not gonna get into that in this video because that's a little bit long. Alright, so let's say w is the multivariable function of these two functions, x of t and y of t. If w is differentiable, then we can assume that this equation is true. So if we divide both sides by delta t, we get this. And if we let delta w and delta t go to 0, we get dw dt is this. And by the way, I forgot to mention that when delta w approaches 0, then delta x and y, they also go to 0. That's another condition that this has to meet for w to be differentiable. Anyway, since delta w goes to 0, then both epsilon 1 and 2 also go to 0, since that's one of the conditions. So we can just cancel, or we can just get rid of these epsilon terms. And rewriting fx and fy, we get this. So this is the chain rule for w, which is a function of two variables, which are both functions of one variable. By the way, here in this partial derivative, it's stating w as a multivariable function with respect to one of its frickin' variables, and over here we're using d instead of del, because if you plug in x equals x of t, y equals y of t, w is really just a function of one variable t. And I hope you're starting to see some kind of pattern here. In if w is a function of one variable, which is a function of one variable, this would be the chain rule. And then if w is a function of two variables, which were functions of one variable, then this would be the chain rule. And if we had w be a function of three variables, which were all functions of one variable, this would be the chain rule. So can you guess what the chain rule would be for if w was a function of four variables? It would be a sum of 4 terms. I'm not trying to write all that right now because that's like way too much, but like, you know what I'm saying. Alright, so now let's take this function w, which is a function of one variable, and that variable is a function of two variables. So we switched it around this time. Well, if this was true, we would have 2 chain rules instead of just one, because we can take w with respect to each of the variables. And then if we had x be a function of 3 variables, we would get 3 chain rules for each of the variables in that's stated in the function x. Again, I'm not trying to write all that, so I just filled it in. So you're noticing a pattern here, right? If w is a function of x and x is a function of n variables, then there are n chain rules, because you can take the partial derivative with respect to any of the n variables. Alright, now so let's assume w is a function of 2 variables, which are both functions of 2 variables. Well, the 2 chain rules that we would have with respect to the variables described by x and y would both have a sum of, what do you call it, 2 terms. And we can generalize this. If w was a function of 6 variables, and those variables were functions of 4 other variables, then we would have 4 partial derivatives of w with respect to each of those 4 variables, which are described by those 6 variables, the 6 functions, and each being a sum of 6 terms, since there are 6 functions of those 4 variables described by w. And now we're just going to generalize it formally. So if w is a function of any amount of variables, x through v, and x through v, all those variables are differentiable functions of the variables p through t. So another finite set of variables. They have to be finite. They have to be finite. They can't be not infinite. So if that is true, then the partials with respect to any one of the variables from p through t would be of this form. It would be given through an equation of this form right here. So let's say the set of variables described through f, let's say we have an n amount of those, and in these variables we have an m amount of these. So there's an m amount of partial derivatives which we can take with the chain rule, and those chain rules each are just a sum of an n amount of terms. And take a look at this. This looks a lot like something. This can just be written as the dot product of these 2 variables, or I'm sorry, vectors, where one of the vectors is all the partial derivatives of w with respect to x through v that are described by f, and then the second vector, its corresponding the components, each of the components correspond to, for example, the first corresponds to x, second corresponds to the second one, the vth one, or the nth one corresponds to v here. So the second vector's components are just the partial derivatives of the variables of f, those functions, with respect to the variable that we're choosing to take the partial derivative of with the chain rule. And what we'll see here, or what we'll notice here, is that this dot product is really just an n-dimensional dot product, where n is, of course, the amount of variables that are described through f directly. So let's say again that we have this w, which is a function of x, y, or just 2 variables, and then those variables are functions of 1 variable. So we already know that this is the chain rule for the derivative with respect to t, and now we know that we can just rewrite this as a dot product of 2 vectors. So we now know that this derivative, this derivative is really just a dot product of these 2 vectors, or in other words, it's just the norm of the orthogonal projection of either of the 2 vectors onto the other. So yeah, I thought this was really cool connection from two seemingly really different parts, because differentiation does not seem to have anything to do with vectors whatsoever, besides the fact that you can differentiate vectors, but that doesn't really, we're not really doing that. Oh yeah, I forgot to mention. So let's say we have this function of x and y, which is the product of x and y, and then x and y are both independent functions, or they could be the same function, whatever. They're just functions of t. Using the chain rule, we get that df dt is this. And if we sub in x of t and y of t for x and y, we get this. And this looks very similar. And it in fact should look familiar because it's the product rule. Yeah, so we've just shown that the product of, or the derivative of the product of two functions of one variable is this without using the limit definition of a derivative and doing all that stuff. Yeah, so that's another reason why the product rule works, because it follows the chain rule. Anyway, yeah, bye.